Okay, this will be example 4. Same instructions, estimate the value of the following limit. And our limit this time is the limit as t approaches 0 of cosine of pi over t. Okay, so to estimate the limit, we need our chart of values on either side of 0. So our chart is going to look similar. 1, 0.1, 0.01, 0.001. And we're going to get our function values for those. Then we're going to plug in -1, -0.1, -0.01, -0.001. And get our function values for those. Okay, I do want you guys to get some more practice plugging in these values into our function. So if you need to borrow a calculator, I can get you one. Yeah. Either way, this one you're not going to have to do that. Okay, let's make sure that we are all in the correct mode. If you go to mode, which is right here next to the second button, in the third row, you should have radian highlighted. If you have degree highlighted, you need to go over to radian and press enter. Okay, so you need to be in radian mode. Okay, you guys should have this first part done first, right? -1, then you get 1 3 times. Okay, you get the same thing on this side as well. Okay, so what does our function value, these function values, what are they approaching? 1. So looking at this, I would say our limit as t approaches 0 of cosine of pi over t equals 1. It doesn't. We're going to talk about why, but our chart makes it look like it does, right? Yeah, if it's a constant function and it truly was constantly 1, then our limit would still be 1. That can happen, but that's not what's happening with this function. I want us to try plugging in a couple other function values, like let's look at f of 1 over 2001. That's that's closer to 0 than anything we've tried here. That's closer to 0 than 0.001. So if we're saying our function's getting closer and closer to 1, or if it's staying 1, then our function value for this number should also be 1. Okay, so if we plug this in, cosine of pi over 1 over 2001. -1. So we went back to -1, getting closer and closer to 0. Okay, what about f of 2 over 2001? Another number that's closer to 0 than anything that we tried in our chart. So this is going to look the same as this one, except changing this 1 to 2. Hold on. Okay, times 10 to the -12. I'm not gonna write all that, but this is a very, very tiny negative decimal. Like this decimal point is actually 12 places to the left. So it's 0.000000000, however many 11 zeros, 51, and make it negative. Definitely doesn't fit into our pattern of ones that we thought we had. Okay, if we were to do one more, let's just 4 over 4001, just for fun. Random, kind of close to 1 decimal, 0.7071, and so on. So we plugged in 3 numbers into our function. All 3 of these numbers are closer to 0 than anything in our chart that we tried. So if our function was getting closer and closer to 1, these should have come out to be 1 as well, and they didn't. So I want us to look at the graph of this function to see what's happening. If you want to look at it on your calculator, here's how you can put it in. You go to y equals, you put in cosine of pi over x. When we graph, okay, it looks like there's something funny happening around where x equals 0. So I'm going to change my window. I want to look at -2 to 2, -1 to 1.2. Okay, so I'm basically just zooming in on the origin. Here's what our graph's doing. So it's kind of having a stroke in the middle where x equals 0. And this graph, because it's so pixelated, it doesn't even really do it justice. I'm going to draw a picture of what it's actually doing just because I think it's fun. You probably put in some wrong numbers on your window. Oh, it did? Okay, well, here's just a fun little graph of what's happening. Whoops, my y-axis is not very straight, but that's okay. Okay, here's what our graph is doing. This is 1. This is -1. So our graph is this is kind of what the graph looks like. Okay, so from looking at the graph, we can see as we move in towards a t or x value of 0, the function starts oscillating really wildly, going back and forth across the x-axis. And it gets like crazier and crazier as you get closer and closer to 0. So it's kind of oscillating kind of nicely out here, and then you get closer and closer to 0 and it goes crazy, and then it's kind of okay as you get on the other side. So our definition of a limit says in order for a limit to exist, the function must be settling down in towards a single value as we get closer and closer to the point in question. So even though our chart made it look like, yeah, the limit's 1, it's getting closer and closer to 1, that's simple, that's easy. This example is just to show you, even though that is happening, it's always a good idea to take a look at what the graph actually looks like, plug it into your calculator and see what it's doing at that x value. Because for the limit to exist, every value that you plug in closer and closer to the x value should be giving you a number, a function value that's closer and closer to some number. It shouldn't be going crazy like ours did when we started plugging in other values that got closer and closer to 0. Those numbers went crazy because obviously our graph is crazy. So what we say about this is because the function does not, whoops, sorry. Because the function does not settle in towards a single number, as t approaches 0. The limit as t approaches 0 of cosine of pi over t does not exist. So this is our Mean Girls moment. The limit does not exist. We win the math decathlon. All is right in the world. Regina George is broken. Okay, does everyone understand why the limit doesn't exist? The function has to settle in nicely in towards a single point, just like our first few examples did. We could look at the graph and we could see that the function clearly approached a certain number as x approached 2 or whatever it was. That doesn't happen in this graph, so the limit doesn't exist at t equals 0. We could probably find the limit if we looked at an x value over here somewhere, because this is nice. The function's nice at this point. We could find a limit where x equals, what, probably -2 or something. But since the x value in question was 0 and our function is going crazy at when x is 0, there's not a limit at that point. Okay, let's take a short break. All right, we've got another piecewise function. Okay, this is a function that is sometimes called a step function. We're not going to actually make a chart for this one. We're just going to look at the graph of this function. You'll see why it's called a step function. Okay, so this function is, the function value is 0 when t is less than 0. So on the left side of the y-axis, where our x values are less than 0, our function is 0. So it's going to be laying on the x-axis here. Okay, when our x values are greater than or equal to 0, the function value is 1. So all of these x values have a function value of 1. So the darker lines is our function. So it looks like a step. That's why it's called a step function. Okay, so we can look at the graph. And if we were to plug in values on the left side of 0, that'd be over here. If we would get closer and closer to 0 on this side, all of our function values would be 0. Right? All of these x values are less than 0, so our function values for all of those values are going to be 0. So our chart would look like x values, and then all of our function values would be 0 every time. On the other side of our chart, or if we're looking at values getting closer and closer to 0 from the right side, all of these x values are going to produce function values of 1. We plug in this x value, we get a function value of 1. Getting closer and closer to 0, we're still getting x value or function values of 1. So our chart, our other side of the chart would look like x values. We're going to plug in all these x values, getting closer and closer to 0. All of our function values will be 1 for every single one of those. So I want to write that down somehow so you know what's happening before we just write the answer. Okay, let's say h of t, which is our function, right, approaches 0 as t approaches 0 from the left. Okay, just a shorthand way of writing what we talked about, looking at this side of 0 as we get closer and closer to 0. So as our t values approach 0, our function values also approach 0. They stay on the x-axis here. Okay, h of t approaches 1 as t approaches 0 from the right. So that's just putting into words what we said when we plug in t values on the right side of 0, getting closer and closer to 0, our function values are always 1. So our function is approaching 1. So if we were to do our chart like normal, on one half of our chart, it would look like the limit is 0. On the other half of the chart, it would look like the limit is 1. So because the function does not approach, because the function does not approach the same value on both sides of t equals 0, the limit as t approaches 0 of h of t does not exist. So for a limit to exist, our function has to be approaching the same value on both sides. So in the last example, our function didn't settle down towards a single point, so the limit didn't exist. On this one, this is a really simple step function. The graph is not crazy at all, but because the function doesn't approach the same y value on both sides of 0, the limit doesn't exist. The function has to be approaching the same value on both sides of the x value in question for the limit to exist. Y. Yeah. Any questions on those? Okay. That's going to be all for notes today.